There's another property of functions that's very important called symmetry. We're going to explore three different types of symmetry. Actually, these are symmetries for relations. And then we're going to narrow it down to two types of symmetry that are specific for functions. Okay, so you'll see behind me here we have three types of symmetry, and just an example of each. I have y-axis symmetry, x-axis symmetry, and what we call origin symmetry. The origin symmetry is a little bit harder to identify. That one we'll talk about in a moment. And so just so you can see, now symmetry is this idea that that there's some sort of reflective property or a part of the shape that is identical on another in another part. Okay, and so this y-axis symmetry, you can see that part of this shape is a mirror image, I should say, maybe not identical, but a mirror image of another part of the shape, okay, or the graph. And so if you were to fold this graph along the y-axis, think of it as a sheet of paper that you fold, the two sides would match up perfectly, okay? When you have symmetry across something like the y-axis, then there will be points that are symmetrical, okay? They'll be horizontally positioned from each other. And what happens is they'll be at the same height on the function, the same y value, but they will be an equal distance away from the axis of symmetry, or the y-axis, okay? So they're going to have the same y value, but they'll be an equal distance away from the y-axis on either side. With x-axis symmetry, you're going to have something very similar, just with respect to the x-axis. You can have sort of a mirror image on either side of the x-axis. Okay, so just like with the y-axis, then that mirror image creates sort of this this folding idea. If you could fold the graph along the x-axis, the two sides of the graph would match up identically. Now, for every point on a graph that has x-axis symmetry, there will be a symmetrical point on the other side of the x-axis. And what that means then is that they're going to have the same fixed x value, but they're going to have two different y values. And the y values are going to be equally spaced across the x-axis, apart from 0, right? So 0 being the x-axis. And so one will be positive, one will be negative. In a similar way with the y-axis, the two symmetrical points, one will be positive, one will be negative, okay, on either side, an equal distance on either side of 0. Okay, so for the y-axis symmetry, you're going to have, for every point here, we'll call one of these x comma y. It doesn't matter which one I call x, y. It's an arbitrary point on the graph. Then there's going to be another point called negative x comma y, also on the graph, okay? One being positive, one being negative. The y values, notice, are exactly the same for y-axis symmetry because they're at the same height on the graph. But the x values are going to be equal but opposite, right? They're going to be the same distance from 0, but opposite in sign. And so, one's negative and one will be positive. And so we would say that for every point xy on the graph, there is another point, call it negative xy, on the graph. Okay, so this will be true for every graph that has y-axis symmetry. In a similar way, for x-axis symmetry, we would say that for every point, now here I'm going to we'll throw xy on here as well. For every point xy on the graph, there is another point Now the other point in this case is not negative xy. For x-axis symmetry, remember you have consistent x values. The x value is fixed. So here your x is the same. Oops. It's the y that changes sign. Right? So it's x negative y would be the other point. So there's another point. We'll call it x negative y on the graph. Okay? So for x-axis symmetry, you have both x, y, and x negative y. So the y changes sign, whereas the x is fixed. For y-axis symmetry, you have x, y, and negative xy, where the y is fixed and the x changes sign. Now with origin symmetry, it's quite a bit different. For every point on the graph, there's going to be a symmetric point, but it's not going to be done by folding. It's still a reflection, but it's a reflection through a point rather than through a line. Okay, it's a reflection through the origin specifically. So if you drew a line segment through the origin that has an equal distance on either side of the origin, you will get a symmetric point. And so this distance above the origin, or above and to the right, is the same as the distance below and to the left. Those two distances are the same. Okay, and so you take a point and you can reflect it through the origin. And that works for every point on the graph. So it doesn't matter if I take a point on the left here, I can reflect it through the origin and I'll find a symmetric point on the graph on the other side. Okay, so this reflection through the origin is a little bit different idea because it's through a point and not through a line. Okay, so now the question is, how do I describe it, verbally? How can I describe that? Well, we would say that for every point x, y on the graph, if you were to reflect that point through the origin, it's going to change the sign, both signs, both the x and the y. So in other words, if you had a positive x, positive y, it would result in a negative x, negative y on the graph, but again of the same distance. Okay, you have to have the same xy distances in order to get that reflection, in order to get the same diagonal distance on the graph. Okay, it's a congruent triangle sort of argument. Now you don't have to have both positives. You could have a graph that's symmetric from the second quadrant to the fourth quadrant as well, that sort of thing. In which case you might have a negative x positive y results in a positive x negative y. But the main thing is that both signs change. Okay, it doesn't matter which one gets the positive, which one gets the negative. And so for x, y on the graph, there would be a point negative x, negative y on the graph as well. All right, and I put the two negatives here because it really just represents the opposite sign. One of these could have been negative. When you then apply another negative, it makes it positive. So it doesn't really matter where I place those negatives as long as both of these coordinates have opposite sign as these. Okay, and so I would write the sentence out for every point xy on the graph. There is another point negative x, negative y on the graph. Okay, so these are our three main types of symmetry. Now, if I gave you a point, let's say I gave you a point 2, negative 3, and I said that's on a graph that has x-axis symmetry, then you could identify another point simply by using this relationship. We'd say this is my xy point, and with the x-axis symmetry, the y value is the one that changes sign. And so that would tell me that 2, 3 is also on the graph if there's x-axis symmetry. Okay, for x-axis symmetry, that would be the case. And so you can kind of see how that would work. If I said origin symmetry, I would have had to change both signs. And if I had y-axis symmetry, I would have changed the x instead of the y and left the y the same. okay? Okay, now, when I look at these, I can immediately apply the idea of a function to two of them, but not to the third. Functions can have y-axis symmetry and origin symmetry, but they cannot have x-axis symmetry. The reason for that is, if a graph has x-axis symmetry, by definition, it's going to have 2 points with the same x value, but different y values. We know the definition of a function is, for every x value, you have a unique y value. Here I have an x value that has non-unique y values. It has 2 different y values, so it violates the definition of a function. It also fails the vertical line test. Okay, so this is definitely not a function. So in fact, as we get into properties of functions here, we're going to not see the x-axis symmetry as often. We are going to experiment with that a little bit more when we get into conic sections later in the course. We are going to work with some relations that are not functions, and x-axis symmetry will be important. But for right now, I'm going to kind of leave the x-axis symmetry behind, and we're going to focus in on the other two, okay, the y-axis and the origin. Now, for y-axis symmetry, we can assume then that y is equal to, and we can do this for really both of them, we can assume that y is a function of x, okay? Now, you can have relations that are not functions that still have y-axis symmetry and origin symmetry, but I'm just saying that functions can only have these two. They can't have x-axis. If we make the assumption then for a moment that y equals f of x, because we're going to be dealing with functions primarily, then these points, you know, in the y-axis symmetry type of function, the point xy is really the point x comma f of x, and the point negative xy is really the point negative x comma f of x. Okay, because the y value doesn't change. But anytime you plug in a negative x, anytime you plug in an x value, the function should represent that x value, right? So this point should really be the same as negative x comma f of negative x, because it's negative x that I'm plugging in at that point, even though the two function values are the same. And so we have this relationship then for y-axis symmetry that f of negative x is actually equal to f of x. The two function values are the same. Okay, so that gives us a nice relationship for the y-axis symmetry. Now, if you consider the origin symmetry in a similar way, for every xy point, or we'll call it f of x, if you change, you can change both of the signs. So you'd have negative x and negative f of x on that graph. Or I'm sorry, this would actually be negative f of negative x. No, it's not. No, that's right. Negative f of x. This is fine. Now, how this works out, these two things are going to be the same. But if you were to plug in, I should probably write this a little bit different. If you were to plug in the positive x, then you would get the opposite sign as you would if you got, I should say that differently. If you plug in the negative x, that would be better. Plug in the negative x, so the output is this negative y. It's the opposite sign of what you would get if you plugged in positive x. So it's the opposite sign, negative, of the positive x as the input. Okay, so what that shows me, what this relationship shows me, is that when I change the sign on the input, it changes the sign on the output. Okay, that kind of makes sense. Change in sign on the output, or input, results in a change in sign on the output. Now, it doesn't matter which side I put that negative on, because, you know, if I divide both sides by -1, it just moves it to the other side. So that's equivalent. but this is the way we usually represent it. And so for origin symmetry, we would say then this is true. F of negative x is equal to negative f of x. Okay. In the next video or two, we'll explore how to use these two concepts, these two function notation types of concepts, to identify whether a function is has one of these two symmetries without having to look at the graph. There is one other thing I wanted to mention before I do that, and that is that we have names for functions that have these types of symmetry. Y-axis symmetry, functions that have y-axis symmetry are called even functions. Okay, so these are called even. And origin symmetry, functions that have origin symmetry, are called odd functions. Okay. Now you technically cannot have both types of symmetry in the same function. If you did, it creates an x-axis symmetry where there is no, where it's not a function anymore. Okay, if you have both of these types of symmetry, imagine this: if you had both x-axis or both origin symmetry, so you reflect across the origin, and you had y-axis symmetry, then you would end up with 2 points that line up vertically. So you can't have both. So you're either going to have even functions or odd functions, or potentially neither if they don't have any symmetry at all. And the reason we pick the words even and odd may become more clear as we move throughout the semester. I'll point out some interesting little facts about that, but I'll save that little tidbit of information for another time.